Hello and welcome back. In this video, we are going to try something new. I have a generated image here, which I'll try to use to tell you a story about how we get to the bottom of the canyon. Imagine a deep, smooth, parabolic canyon. It's not exactly like that in the picture, but imagine just let's imagine that it is. And down here, we see the absolute minimum of the valley, and here we are standing trying to get down to the bottom of this valley or canyon, and here is the chest of gold we are looking for, which is the optimum weights for our Adeline network. Now imagine that we have to walk down this canyon in a pitch black fog carrying a lantern that flashes on and off randomly. Okay, so every time the lantern flashes, a single sample K, that's what we are going to think. Anytime a lantern flashes, so all we see is only a tiny patch of mud directly under our boots, right here. And with just that knowledge, we have to decide which way we are going to step. And because the ground is uneven, a single step could help us. It could go left or it could be on the right hand side to take the path, uh, and we then also have to take we also have to know how far we are going to step. So that's the step size alpha. The point to note is, if the stride or the step is too long or frantic, we will widely stomp back and forth, climb up the opposite side of the canyon walls, and completely get lost in the mountains. But if the step size is small and controlled, then the random left and right deviations that we'll do while walking downhill would cancel out. And on an average, the gravity of the canyon slopes will gently drag us down to this the minimum of that particular surface. All right, so with that, now let's get back into the math part of this. In our last video, we derived the LMS learning rule, and we saw that what Widrow and Hoff did was they bypassed the heavy statistical operator E, which is the expected value, and created a fast real-time formula that updates the weight knobs based on just one single sample at a time. That's what the K we have been talking about. But now let's be honest, that feels like a massive gamble. If you train a network using a single noisy random samples, how do you know it won't just wander around circles forever and never get back to the bottom of that surface, or the minimum of that surface? How do we know it will actually find the true bottom of the error bowl? So today we are going to dive into a beautiful formal proof that will tell us that on an average this noisy algorithm tracks the exact same path as the steepest descent method that we have seen previously, and it settles perfectly at the optimum minimum. So to start the proof, we have to establish one ground rule that Widrow and Hoff assumed, which is that our current weight xk, so this is our current weight xk. Remember, this x was would have both w and the bias. This is a result of all small adjustments that we have made in the past from the data samples. For example, it would have the input, it would be input k minus 1, maybe input from 2 steps back k minus 2, all the way up to our starting point. Okay, now if we assume that each new piece of data that is passing through our system is statistically independent of the previous data, then our current weights, they are completely independent of the next incoming data as well, zk. So let's keep this in mind, because it means mathematically we can separate our weights from our inputs when we take the averages. Let's look at the proof right now. So we start with our familiar single sample LMS update rule. So single sample LMS update rule, which is xk plus 1 is equal to, these are the new weights, is equal to xk, these are the old weights, plus 2 alpha ek zk. So this is the error, this is the input, and you remember input will have the one for the bias as well. Now what we want to do is find out what happens to these weights on average over time. And so to do that, what we do is we apply the expected value operator E to both the sides. And so what we get is E x k plus 1 is equal to E x k plus 2 alpha E E k z k, like so. Now let's we'll go ahead and expand this by substituting this term right here. We know that ek, so we know that this ek is equal to tk minus x k transpose zk. So we have seen this previously. So we will put that right in there. So I'm going to start writing from here. E x k plus 1 is equal to E x k plus 2 alpha, that stays as is. Now is the substituted part E, we create this bracket, and here we write out the terms. So let's, before we jump to this, why don't we keep it simple? We'll just leave this as E. I was going to expand it right away, but we'll first put the values in there and then expand it. This is going to be tk zk, or tk, sorry, this is going to be my mistake. This is going to be simply this, right? tk minus xk transpose zk zk, and then we can expand this. We have E xk plus 2 alpha E, and so what we do is multiply this by this by this, so we get tk zk minus xk transpose zk into zk. Now because the expected value of a difference is the difference of expected values, we can split this two separate brackets, which gets us E xk plus 2 alpha E tk zk, that's 1, so we have breaking this here, minus E xk transpose zk, and then we have the zk that's outside here. All right, so now let's look at the final term in here, which is this one, the term xk transpose. So this term right here, let's use a different color. So this term right here evaluates to a single scalar value, and so in linear algebra, a scalar multiplied by a vector can be written in any order. So we can swap their positions, and instead of writing it like this, we could also write this as Z transpose K dot X K. So with this, we can now rearrange what we have and write it out as this is going to be equal to EXK plus 2 alpha E, then this is TK ZK minus E, and this is where we swap these. So what we get is ZK ZK transpose, and we pull this XK out, and that is what we get. So this is where our independent assumption pays off, because now what we can do is, because xk and zk are independent, we can split the expectation of the product into the product of their individual expectations. This one, you'll see what I mean. So what we do is, before we go there, another point to make is, we note that this part E, expected value of tk zk, this is nothing but our fixed this is our fixed cross correlation matrix that we saw in the previous video. This is the H, and on the other side, this part right here, this is our fixed input correlation matrix, and that we denote by the letter R. Okay, so this is what we have. We can substitute those in here, and what that gets us is EXK plus 2 alpha, and this part becomes just H, and then the other part becomes just R, and then we split this. So we are essentially, as we said, we'll split this, and so we are left with the expected value of xk. Right, and now we can group this xk right here and xk right here to get I minus 2 alpha 2 alpha R expected value of xk plus 2 alpha H, and this is, I stands for identity matrix. So that's just saying that that's value of 1. If you multiply any matrix by that, you get the same matrix back. Alright, so with this, what we see now is a recursive feedback loop. With every step, our average weight vector is multiplied by this. So this is our weight matrix, average weight matrix. This is our average weight matrix that is multiplied by this part right here, which we can say that's the matrix modifier. Now think of this like multiplying a number over and over again in the calculator. If we multiply a value 0.9 by 0.9 repeatedly, what it does, it shrinks and stabilizes down to a clean destination. But if we multiply it by 1.1 repeatedly, then it can blow up to infinity. And so for this system to stabilize and converge, the scaling factor of this matrix must be strictly less than 1. And in matrix algebra, we measure the scale using eigenvalues denoted by lambda. So the eigenvalues of our system matrix are 1 minus 2 alpha lambda I. So this is what we have, where this lambda, this part right here, it represents the eigen values of our matrix R, which is right there. You see the similarity between I minus 2 alpha R and 1 minus 2 alpha lambda I. So with that in mind, what we can do is to prevent our weights from exploding, we need this factor to stay inside the boundary of unit circle. What I mean by that is we need this 1 minus 2 alpha I needs to be greater than 1. So if we subtract 1 from both sides, what we get is minus 2 alpha I greater than minus 2. You divide by 2, and so we get uh, sorry, this was I missed the lambda I here. So alpha lambda I, not alpha I. And so what we do here is lambda I, so this goes away, and so this becomes less than 1. Therefore alpha is less than 1 divided by lambda I. Now this is an important relation. You may have seen this previously in one of the videos. And that is that to guarantee that this condition holds true for every single axis of our data, our learning rate alpha, this is the learning rate, it has to be smaller than 1 divided by the largest eigenvalue of our matrix, and so that would be the lambda max. So this is a beautiful convergence theory. Earlier in one of the previous videos, we found that the standard steepest descent method, it stays stable if lambda it stays stable if lambda was less than 2 divided by lambda max, where this was the eigenvalues of the Hessian matrix A. Now because the linear neurons Hessian matrix A is directly equal to 2R, the stability limit of our real-time LMS algorithm is also the same. So that's a big find we have here. Now one final step before we end the video is, if we pick a safe conservative learning rate that satisfies this condition, then what happens when our system reaches a steady state, right? So if we imagine E x E, and let's say x k plus 1 is equal to E x k is equal to E x s s, then this E x s s is equal to, so let's write it down, E x s s is equal to I minus 2 alpha r expected value of x s s plus 2 alpha h. Now we distribute the E x s s across the brackets, and so what we get is E x s s s is equal to E x s s minus, we are essentially multiplying it all here, 2 alpha r E x s s. So we are trying to get back to the original x star is equal to r inverse h, that equation, plus 2 alpha h. We subtract this from both the sides, what we get is 0 is equal to minus 2 alpha r E x s s plus 2 alpha h, and Now we move the negative term over to the left hand side. What we get is, so we bring this down here, we get 2 alpha r e x s s is equal to 2 alpha h divided by 2 alpha on both sides. We get r e x s s is equal to h. So these two cancel out essentially, and so in the end we can see that we are getting close to, so what we have seen previously. This is -1 h, and that we know that we have seen this denoted as x star. So that's the complete proof. So this final relation right here, it shows us that even though LMS algorithm takes noisy, frantic single sample steps in every single iteration, its long-term expected trajectory, its long-term expected trajectory is mathematically guaranteed to land to the absolute theoretical minimum of the performance index. So if you are walking down the foggy canyon, as we saw in the picture earlier, you'll successfully find the chest of gold, the optimum weights every single time, as long as you keep the alpha, that is the step size or stride size, controlled by the eigenvalues of the data that you have, which we saw here. And finally, let's look at a example where we can actually see this in on this working. If we have a input vector p1, and this is referring to the example of orange and apple vectors that we have also discussed previously in the series. If you have an input vector p1 which has values 1, -1, 1, and the associated target with it is t1, which is simply -1. That's the first input, and then we have a second input p2, which is equal to 1, 1, -1, and the target t2 is equal to just 1. With this input and target, we can calculate the values for the input correlation matrix R. Input correlation matrix R that we have been seeing so far. So R is equal to the expected value of P transpose, and so this would be 1/2 P1 P transpose plus 1/2 P2 P2 transpose. This is P1 P1 transpose. So we write that out, 1/2, and this is 1 -1 1. Sorry, this is -1, my mistake. And we transpose that 1 -1 -1. The second one is again 1/2 1 1 -1. Transpose that 1 1 -1. And if we solve this, this would be 1/2, and this, and if you go ahead and solve this, I'll do for this one. 1 times 1 is just 1, 1 times 1 is -1, 1 times 1 -1 is 1, and so we'll get a matrix that's 3 by 3. This is -1 plus 1 plus 1. Again, this will be the same, -1 plus 1 plus 1, and here we have 1 1 -1. You multiply 1 1 -1, this will be -1 -1 1. Now we just take this 2 out and add these 2. So 1 plus 1 is 2, 1 -1 plus 1 is 0, -1 -1 is -2, -1, this is 0, this is 2, this is 0, this is -2, this is 0, and this is 2. And so we divide all of this by 2. What we get is 1 0 -1 0 1 0 minus 1 0 1. Right, awesome. So this is the input correlation matrix R that we have, and for this we need to calculate the eigen values. To save time, I already have them. Lambda 1 is equal to 1, lambda 2 is equal to 0, lambda 3 is equal to 2.0 or 2. So as you can see, this is the largest eigenvalue that we have for R, and that is what we are going to use to uh, get our learning rate alpha. So alpha, which is going to be, this is the learning rate, is going to be less than lambda max, and so this is 1 by 2, so 0.5. All right. And to be safe, well, let's say we pick a value of alpha that is much smaller than this, and we will say that we pick a value of 0.2. Using this, we can now calculate our values for the predicted values A. So let's say in the first case, when we start out, the W vector that we have, let's say we pick this as our learning rate, and then we need to pick the values for W. For W, we say that the values for W that we have are just 0 0 0, or we could write it this way, 0 0 0. And with that, when we say A, we try to calculate A0. This is going to be equal to W 0 P 0, and so uh, P0 is, this is equal to W0 P1. P1, that's the input 1, and what that gets us is 0 0 0. That's what we initialized with. Or 1, P1 is 1 minus 1 minus 1, so that's what we write here, 1 minus 1 minus 1, and that gets us value of 0. 0 times 0 plus is all 0, and therefore the error in the 0th iteration is T0 minus A0. That gives us the error, the target for T1 minus A0 value we calculated for A0, and target for P1 is minus 1, so this is going to be minus 1 minus the A0 value is 0, and so the error that we get is minus 1. Therefore error here is minus 1. We use this value now to update our weights. So for the second iteration, let's change the colors a little bit. Let's pick this one. So for next iteration, we have W1, which is going to be equal to, so remember that these are the new weights, right? These are the old weights. This is W0 plus 2 alpha E0 P transpose 0, and here the old weights that we know are 0 0 0 plus 2 times alpha, which is, we selected 0.2, could be any other number, and the error we calculated, it was minus 1, and we have the input P minus 1 transpose, and if we go in and solve this, this will be 0 0 0, this becomes this becomes 0.4. Then let's put the minus sign here, so 0.4 times or let's leave this as plus 0.4, and if we transpose this, it will flip horizontally, so 0.4, this is minus 0.4, minus 0.4 times 1 is minus 0.4, minus 0.4 times minus 1 is 0.4, and this is 0.4, and in the end then what we have as updated weights is minus 0.4, 0.4, 0.4. So these are the updated weights that we have. Now what we will do is remember why we chose just P1. Here is, we can say that that's remember the always the K. We picked this input. Let's say next we picked this input, then we picked a pick P1 again, then we pick P2, and we can go on and on. And so this time what we'll do, let's imagine that this time uh, we are going to look at the next data point, which is Apple, which is P2. And for that, let's say this is Apple P2, and we calculate A1. So A1 is equal to W1 W1 P1, and in this case W1 is minus 0.4, 0.4, 0.4, and the P1 is in fact this is in fact the input P2, and that is going to be equal to 1. What is it? The 1 1 minus 1. So we say 1 1 minus 1, and we calculate the predicted value, which is going to be, this is minus 0.4 plus 0.4 minus 0.4, and so these cancel out. So we get A1 is equal to minus 0.4. So that's what we have. Now it's time to uh, calculate the error of this iteration. So we calculate E1 is equal to T1 minus A1, and so our T1, the target for P2 was 1, and so we use that. So target for P2 was 1, the value we calculated was minus 0.4, so our error has increased to 1.4. We use this error now again to update our weights. So in the next iteration now we update our weights again. We say W2, this is the new weights, is equal to W1. These now become the old weights plus 2 alpha e to E1 dot P transpose 1. See that we the inputs that we are using change. So in this case we again have the same W1 that we calculated earlier, which is minus 0.4, 0.4, 0.4 plus 2 alpha. Now the error is 1.4 that we calculated, and the alpha is 0.2, so we write that there. And for the p value, so here we are using P2, this is 1 1 minus 1, that's what we'll use. So 1 1 minus 1, which is 1 1 minus 1 right here, and if we calculate this, we get a value of 0.16, 0.96, and minus 0.16. Again we present this system with P, let's say we present it with the orange, which is P1, and so we calculate the A2 again. We use W2 as the new weights, P2 that's the iteration, and that is what we are essentially trying to do, is use these new weights and dot that with the inputs P1. And so when we do that, we have 0.16, 0.96 minus 0.16, and here we have 1 minus 1 1, that gets us a value of minus 0.64. Again the steps repeat. We go back and calculate the error with this. This is going to be T2 minus A2, and so this is going to be T2 in this case is going to be the target for the input P1. So target P1 minus A2, which we calculated above. So this is going to be uh, -1. This is going to be -1 minus minus 0.64, and so this time the error is going to reduce because the signs will flip here. So -1 plus 0.64 gets us minus 0.36. That's the new error that we have. Okay. Well, it's time to repeat all the steps again, and I will stop here. We would have to calculate the new weights again. So these are the new weights equal to, these are the old weights. Again, the formula stays the same: 2 alpha E 2 dot P transpose 2. And if you plug in all the values, I already have the final weight. I already have the weights here. We get 0.016, 1.1040, and minus 0.0160, and so on. So you continue this, and eventually the algorithm would converge to W infinity is equal to 0, 1, 0. So that is the whole story about convergence for the LMS algorithm. I hope in this video you got a detailed insight into how the convergence works for the LMS algorithms. How do we find the optimal learning rate alpha, and how we update the weights using the errors in this final example. If you have any comments or suggestions, please do let me know in the comment section below. Also, let me know how you like the initial story at the beginning of the video where we used a image. uh, Please like, share and subscribe. I hope to see you all in the next video. Thank you.